and giving you an example of what goes on, how this is going to work. If you're told it is a normal distribution, that is a godsend. Okay, so number one, you'll be told that your data is normal, or it's normally distributed, or you have a bell-shaped curve, or you have a symmetric relationship. If they tell you that you have a normal distribution, then that gives you the rights to be able to use the 68, 95, 99.7 specialized operations. They will always have to give you what the mean value is going to be and what the standard deviation value is going to be. So let's say that we were measuring the heights of 14-year-old girls, and we collected a rather large sample, and we measured them and we processed them by dumping the numbers in our calculator and finding out what the mean and the standard deviation was, and we found out that the mean height of those 14-year-old girls was 51 inches. Now, I'm not saying that that's the actual height, I'm just making up some numbers in here. My sample could have had 51 inches in it. That doesn't mean that every 14-year-old girl is 51 inches. And obviously, not every girl in my sample was 51 inches, although it's possible that would be an extremely unusual situation. So there was a difference that was kind of averaged out. So the average distance in terms of heights was, let's say, 1.5 inches. Those are real world measurements. And if they are real world measurements, then for our purposes, we're going to see those values listed on one side of our axis scale, probably the bottom side, which means that I was told that they were centered at 51. So I know that this value right here represents where I would expect to see a 51-inch 14-year-old female. If I am not exactly 51 inches, then I'm either above the mean or I'm below the mean. If I start looking at standard steps, the standard steps that we take are called standard values, or called z-values. So there is a standard scale that we deal with, also called the z-scale. The z-scale exists to measure standard deviations, not inches. So 1 full standard deviation and -1 standard deviation, forward, backward, so to speak. That would mean that if I were 1 standard deviation of height greater than 51, that I would have to have had a height of 52.5, because I would need to add a 1.5 sized step to get to that first point. If I were shorter than average, then I would have to subtract a 1.5, which would put me at 49.5, because I'm moving in a negative direction back here. So you could actually create the real world values on any scale that you were given if you knew what the central value was and what the standard deviation was. And that's going to allow you to answer every question that we ask about standard scale, standard deviations, and normal distributions. And what that would tell me now is that inside here is where I expect to see 68% of all of the data. If I would visualize cutting out this section right here, I would find out that that would take 68% of all the area that was involved in that curve. Or that if the people were normally or equally distributed in there, that I would get 68% of my people. If there were 100 people in my sample, I'm expecting 68 of them are going to have heights that lie between 49.5 and 52.5. Now that doesn't account for everybody, but it accounts for a fair portion of them. Some of those people are above average height, some are below average height, but they're not far enough above average that we do something special for them. or they're not short enough that we do something special for them, or we do something different with them, so to speak. It's just a marking that is used for being able to categorize people. If we take a second step out there, if we go out to 2 standard deviations above the mean, or 2 standard deviations below the mean, that means that we would take another 1.5 unit step, taking us now to a position of 54, or we would take another 1.5 step backward, which would take us to a value of 48. And we would say then, between 2 standard deviations above the mean and 2 standard deviations below the mean, I'm going to have captured 95% of all of my data. 95% of the 14-year-old females in my sample would be considered to be expected. The heights were expected. I wasn't surprised by that height. At least I didn't fall over dead on the ground and faint because I saw someone that was tall or small. I might have raised a little eyebrow and said, "Oh, you're shorter than I expected to be," or "You're taller than I expected you to be." But you still haven't gone to a threshold of being remarkable yet. If we move to 3 standard deviations above the mean, or 3 standard deviations below the mean, I guess I should put those in the right place, since I told you I was going to put all my standard deviation markings on one side, then that would mean that I've gone back yet another step in the problem. So if I've gone forward another 1.5, now I'm talking about a value of 55.5. And if I go backward another 1.5, now I'm talking about a value that's 46.5. I now say that I know in here, in this section, where I'm looking at the distance between 3 and -3, that I have 99.7% of all of the possible heights. Now there's still some area left over there, but let me explain to you what these values do for you in a context that maybe you can put a picture to it. You are subjected to someone's interpretation of this 68, 99, 95, 99.7 rule almost every day of your life. You see some effect of it. I'll give you one easy one. Car insurance. Most of us pay a standard rate for car insurance. It may be more than we want to pay. Why might some of us pay more? You maybe are a little bit better risk because you cost the insurance company money because you got in an accident and they had to pay. So now they're saying, well, we're going to get our pound of flesh back from you, so they raise your rates, correct? You might be, okay, well, we'll forgive your first accident, and you've been a good driver, but not a good enough driver yet for us to give you a substantial discount or something. You may be over here, in which case they say, sorry, but your rates went up a little bit. If you continue to have accidents, you move into another category. What happens when you move into the next category? They go up even more, and is it possible if they go too far that they get this, that you get this letter in the mail that says, we're dropping you. Now you're gonna go find somebody else, right? Okay. Grades. These are the C's. These are the people that pay their own way through school. These are the people that are above average. They might be getting a partial scholarship. These are the people that somebody's looking at and saying, the people that are out here, because we don't stop at 3. These do go on forever. So you can have a standard score of 4, 5, 6, 7. It doesn't ever end. It's just you're getting a smaller and smaller segment of the population out there. But there are some people at this university that are enjoying a full ride scholarship. Is that true? Okay. And we might wish we were them, but they also have some requirements of that. Yeah, I know, it's ghastly. Okay, let's go back to the insurance analogy. If you've been a good person and have gone 4 or 5 years without any accidents, without any claims against you, might it be possible that your rates go down? There are some insurance companies that actually advertise that you're getting a good driver discount. I wish I had Dennis Haysbert's voice, because that's our real deep voice. Says that you get the good driver discount, okay? So great, you get this good driver discount sitting out here, meaning you're paying less. And there's one company that still advertises a vanishing deductible, meaning you've been such a good driver that we're going to start knocking money off your deductible so that when you do have your first accident and it costs us money, we're not going to charge you for what's going to happen to your rates. Next time they're going to go up a little bit. You have to earn the right to be a good driver again, right? Okay? So in this case, these are some people that are getting the good driver discount. And these are the people out there that are getting that vanishing deductible or saying that I don't have to pay any deductible if I get in an accident. It'd be nice if the insurance company said, you're never going to have to pay insurance again, but it doesn't work that way, does it? They want their money. Go to a great concept. You may be below average, but you might not be so below average that we're requiring something special of you. Are some people who are, by someone's standards, and don't raise your hand if you are, required to take classes that other people aren't required to take?